Awesome. Thank you, Imogen, for a really kind introduction. I like when people talk a little bit about themselves and their history before they give talks, so I'll just do a couple of slides, but Imogen's done a lot of it for me. Today, I'm really excited to share with you the work that I've done on using geochemical data to constrain ice sheet histories over Greenland during the Pleistocene. I have to say that I would not have been able to complete this work without all of my co-authors, although all of the flaws, of course, are mine. Like Imogen said, I'm originally from Portland, Oregon. I did my bachelor's in physics working in Antarctica, my master's in geosciences at UMass Amherst, working in an organic geochemistry lab on a record in the Arctic. And then for my PhD, I kind of fell in the middle. I decided I wanted to go back into something that was computer-based, but stay in geoscience. So I've been working on ice sheet modeling with my supervisor, Rob DeCanto. Like Imogen said, what else do? I tweet maybe kind of a lot. I've been involved in fieldwork both at an ice core site in northern Greenland as well as aboard the JOIDES Resolution with Amelia and Imogen. I do outreach for high school students and undergraduates. Here's a picture of my undergraduates this summer on a STEM Seas expedition. STEM Seas is a really fantastic program that gets undergraduates to go out at sea on UNOLS vessels, and they're always looking for graduate student mentors. So if you want to talk to me about that, that's something you can do. And then I do some work advocating for diversity and inclusion in the geosciences. Like Imogen said, we started this lecture series at UMass called Bridge. The idea was that we would just like to see more early career people from underrepresented backgrounds being invited to talk about their science at institutions. And as in addition, they come and give a talk about the broader impacts of their work or narratives about their entry into a scientific career. So we've had great talks about being a single parent in STEM in graduate school from someone who also gave a really cool talk about soil science. And so the point of this is to try to show that scientists are people and ensure that across our departments, in the College of Natural Sciences at UMass, there's 12 of them, we're getting diversity in our lecture series. I also do a lot of work with AGU, kind of in a similar vein, and I'm excited this year at AGU, if you're going to be there, we have our first ever town hall celebrating the contributions of queer geoscientists over the last 100 years. That's on Thursday, and we have a really exciting session in the education section of AGU called The Next Generation of Geoscience Leaders about activism, outreach, and diversity inclusion efforts, all by graduate students and postdocs. But everyone is invited to attend and support people doing that kind of work. And I think that kind of work is really important because the questions and problems that I study are questions and problems that are going to require a large swath of society to be engaged if we're able to tackle and weather them in a way that's sustainable. I work a lot on ice sheet modeling, and the main impact of ice sheet modeling is sea level rise. I always, when I give a talk, I try to update it with a local impact of how sea level change impacts somewhere. And I have to say, this is probably the most dramatic example that I've ever been able to use. So thanks for that, but also I'm sorry. Sea level rise is going to have a lot of impacts on our societies in the next 100 years. For those that were today at the dean's remarks before the fellowship luncheon, I guess Florida is projected to be the #1 state in terms of the economic impacts of climate change by 2100. So it's very important to understand. We also, I want to point out that the recent report on the changing cryosphere has revised the mean estimate of sea level up by about 10 centimeters to 0.84 meters by 2100 for the global eustatic sea level rise, which is a reasonable amount and will have a big impact on coastlines. However, when it comes to predicting what sea level will be, even in the year 2100, we're still sort of plagued with uncertainty. And one of the main reasons for that uncertainty is we don't know how ice sheets will respond to a changing climate. This is a figure from some of my supervisors' work, just focused on Antarctica, but showing that even under just the uncertainty in climate forcing over the next 500 years, there are very different future trajectories in terms of how much the Antarctic ice sheet might contribute to global sea level. And so improving our understanding of this process is critical to how society will respond. One of the best ways we can try, in my opinion, to improve our understanding of how ice sheets will respond in a warmer world is by actually looking to paleoclimate. And so the geologic record provides examples of times when both the Greenland and the Antarctic ice sheets were smaller than their present day in response to changes in Earth's orbit and changes in CO2. This is a summary figure by Andrea Dutton from a couple of years ago where they compiled the estimates of sea level change for 4 past warm intervals. And what we notice is that even at levels of CO2 that are similar to present day, if we go back to the Eemian 125,000 years ago, or MIS stage 11, sea level was considerably higher, something between 6 and 13 meters, associated with relatively modest increases in global mean temperature. And so understanding the processes and the timescales over which that happened is going to be critical to predicting our future. And what I'm going to talk to you today is how we can use models of ice sheets to understand the processes that drove these kind of collapses in the past. So I'm going to talk to you about 2 studies in the course of this talk. Hopefully we get through in a good amount of time. The first, looking at the last deglaciation in detail from 20,000 years ago to the present, and then the second, applying similar techniques to look at ice sheet stability over the last 800,000 years. So many of you are really familiar with how ice sheets work. I'm sure you have a lot of good talks from your faculty who work on this in the department. But just as a little reminder, this is a schematic of an ice sheet that we've just cut in half. In an ice sheet, we have 2 main areas that matter for the mass balance of the ice sheet. We have the area where snow is accumulating every year, the accumulation zone, and we have the ablation zone. And the place where those 2 areas meet is called the equilibrium line, where you have no net mass change over the course of a year. The ablation zone can include processes like direct surface melting, but you also have calving of icebergs to the ocean, and in places where we have large ice shelves, we have direct melting at the ice-water interface, which is proportional to the amount of warm water and basically the heat that's available from the ocean to melt the ice. In the rest of this talk, I'm going to be utilizing a lot of data that come from a specific kind of measurement. And so I wanted to introduce you to how this measurement is made. This is not a measurement that I make, but one that my collaborators make, and one that we are trying to use as a constraint on how the ice sheet model evolves. So the common theme for the rest of this talk is going to be using cosmogenic isotopes as tracers of ice sheet behavior. The way that this works is that Earth is constantly being bombarded by cosmic rays from space, and when those cosmic rays interact with oxygen inside of a quartz mineral, they can convert that oxygen to a radioactive isotope of beryllium called beryllium-10. There are other processes like this that make other radiogenic minerals, like aluminum-26. But the general idea is that when you have an ice mass that shields bedrock, you have no production of these isotopes because these cosmic rays attenuate very quickly in any kind of cover like water or ice. But when you have a bare bedrock surface, you're able to produce these molecules in situ, so for as long as it's covered, they begin to accumulate. And people have modeled the way that these isotopes accumulate both in space and in time. And so if we look in space, we have this upper row of figures which shows the production of beryllium-10 atoms as a function of depth in the rock column. So you can see that this is a logarithmic scale on top. The most of the production of these isotopes occurs in the upper meters of the rock column, but you can also get some production further down. The useful thing about having multiple different isotopes is that the ratio between them actually changes with depth and changes with time as well, because they have different half-lives. If we go to look at how this plays out as a function of time, you can see these 2 different examples, a purple line and a green line. The purple line showing how beryllium accumulates if you have a 10,000 year exposure interval. So here you can see exposure happening, and then once the area is ice covered again, you quickly begin to attenuate that signal. And the other showing a long interglacial. So when you have 200 years of exposure, you accumulate a lot more beryllium, and then with cover, you're beginning to lose that. And you can see how that affects the ratio as well. So we're going to be using those data in the rest of the modeling that I talk about, as well as climate modeling, which is going to provide us the boundary conditions for running an ice sheet model. So the way that this climate modeling works is that we have a regional climate model which we tune to the present day climate, and the benefit of that is that we're then able to run the same climate model for paleo scenarios when we know the boundary conditions but we don't know the exact climate of the ice sheet. So the way that we do this on the left-hand side is a reanalysis product from RACMO, and on the right-hand side is our regional climate model run with modern-day conditions. And you can see that we capture the main features of both the temperature and the precipitation, with enhanced precipitation along the southwest coast where the storm tracks are, as well as more precipitation on the west side and a very arid northeast under modern-day boundary conditions. So what's nice about this is that we can then take this back in time and run the model for periods where we know the boundary conditions but not the climate. We also are using an ice sheet model, and this is an ice sheet model that my supervisor and Dave Pollard at Penn State developed. It's a three-dimensional thermodynamic hybrid shallow ice, shallow shelf approximation ice sheet model. And the sort of main points you need to know about it is that it compares well with other continental scale ice sheet models at simulating the present day ice sheet, and it's flexible enough that we can use it to run for long integrations and study how the ice sheet has responded to past periods of climatic change. So now we're going to move into part one of the talk, where I'm going to use these methods, the beryllium and the climate modeling, to investigate an outstanding uncertainty in how the Greenland ice sheet responded to the transition between the last glacial maximum and its present day size. So there was these dots on the figure here indicate places where beryllium-10 measurements have been made. And there's now in a database almost 1,000 of these beryllium-10 measurements, which tell us how long that area has been ice-free. So during the last glacial maximum, most of this area was ice-covered, and as the ice began to retreat, many of these land surfaces began to accumulate beryllium, and that has left its imprint in the cosmogenic isotope signature. However, when the authors of this study looked at the timing of ice sheet retreat, they found that it didn't occur at the same time all around the margin. They found that ice sheet retreat occurred much earlier in eastern Greenland, and then a little bit, about 1,000 years later in southern Greenland, and 1,000 years later than that in the west, suggesting that the ice sheet might have been sensitive to different forcings in different sectors. And so we wanted to do some ice sheet model experiments and use these data as constraints to try to understand what processes might have been at play in driving this transition. So I'm going to talk to you about three different ways that we've tried to explore the sensitivity of the ice sheet to different uncertainties in the deglaciation climatology. The first is we're going to use two different domains, one where the Greenland ice sheet exists on its own, and another where you have buttressing from the Laurentide ice sheet. So thinking about the role that different ice sheets buttressing one another play in determining the timing of deglaciation. We're going to use our regional climate modeling approach, where we've essentially updated the boundary conditions every 1,000 years and predicted the climate for everywhere in Greenland. And then we're going to use two climatologies that are based on ice cores. So ice cores give us a record of climate over the last, in Greenland, 125,000 years, but they only tell us about certain spots, and all of those spots are high up on the ice sheet. So there's a question about whether or not the margins, where most of this melting is taking place, the processes there that are determining climate there are the same as the processes that determine climate on the top of the ice sheet. So we're going to use all of these different approaches and use our data as constraints to see which ones work best in which regions. I keep clicking on this, but it doesn't work. The difference between two of our ice core climatologies that we're using is we make different assumptions about seasonality. So when you use proxy data, there are often uncertainties in the season that you're capturing in the signal. And in ice cores, we usually assume that we're getting some sort of mean averaged isotope signal because you have precipitation and exchange of isotopes with the air occurring year-round, at least in Greenland, where the air is relatively humid. So we use two different assumptions about seasonality in the past to generate forcing for our ice sheet model. In this fixed scenario, which is red, you have a change in temperature from 20,000 years ago until the present day, which is the same in every month. So the winters are just as much colder as the summers are. Whereas the other scenario that we're using, which is in blue, we have separate climatologies for the different seasons. So this June, July, and August summer temperatures are actually less cold during last glacial maximum than the winter, and in the winter time we have much colder temperatures, which is something people have argued for the last glacial maximum, that there was a stronger impact on winter temperatures than there was on summer, but we wanted to see which of these would actually give us a better fit with the data that are available. And so in order to make these climate reconstructions, we've used ice core data from multiple different sites, as well as modern spatial patterns to fill in places where we don't have ice core data, and then a seasonality that's based on a different climate model which ran continuously for 21,000 years with coupled ice sheets. And so these are the kind of analyses that we're going to do. If you use a variable seasonality and a fixed seasonality with that ice core climatology, you actually get a very different evolution of the ice sheet through time. So you can see 12,000 years ago, 8,000 years ago, and 4,000 years ago, where the margin is very different between these two simulations. And the idea of the analysis that I'm about to present is that we can use all of these beryllium-10 measurements from around the margin to tell us which of these scenarios is the more likely the reality. When we do that for just the variable climatology and the fixed climatology experiment, these are the results. And so going from Johannes V. Jensenland, which is in the northernmost part of Greenland, and then all around the margin in a clockwise sense up to Thule, which is here, we have the variable and the fixed scenario. And here I'm showing in the text the percentage of beryllium-10 data, which we nail within 1 sigma, and then in the parentheses, the fraction that we nail within 2 sigma. And then the darker colors indicates that that experiment captures a bigger proportion of the data than the other one. And you can already see a spatial pattern begin to emerge when we just use this variable seasonality versus a fixed seasonality experiment. You can see that for most of the east coast of Greenland, we get a better fit with this blue model, the variable seasonality model. When we get to Nuuk, which is here in the southwest, we begin to get a better fit when we use a fixed seasonality. But once we get high enough just past Disco Bay, which is right here, we start to have a better fit with the variable seasonality again. So we're already starting to see some spatial patterns in terms of what the data might be responding to. I want to briefly say or show you the difference between one of the other experiments that I described, that we can either use a Greenland which is sort of restricted to itself. So here's the modern Greenland that we capture with our ice sheet model. If we go back to the last glacial maximum using just Greenland as the domain, we get a Greenland that extends out onto the continental shelf in most places. But if we allow the ice sheet to couple with a Laurentide so the Laurentide ice sheet is coming across Nares Strait here from Baffin and Ellesmere Islands. If we allow those two ice sheets to couple, you see we get a lot of buttressing and the development of a huge ice shelf which extends down into Baffin Bay. And so this is the same climatology but a change in boundary conditions that radically affects the amount of ice that we're able to put on Greenland during the last glacial maximum. So here are the results of all 4 of these different experiments that I described in terms of how much surface melt there is and when it begins, as well as their total ice equivalent. And you can see on the left-hand side here a simulation of one of these scenarios. It's actually this first one, the variable climatology, where as time progresses from 20,000 years ago until present, the ice sheet margin changes. You can see on top of that we're also calculating where ice is flowing, which is a function of the temperature of the ice and the basal thermal state, as well as the surface slope. Excuse me. And so these changes in the ice sheet margin position are driven by when we begin to get surface melt in different regions and the overall evolution of the ice sheet. So now what I'm going to do is take these 4 different scenarios, which you can see differ a lot in terms of when melt starts and when you get the most volume change, and compare them against our database of data altogether. And when we do that, this is the picture that begins to emerge. And so here are the final configurations for 4 different experiments where we've just changed one thing. And in the red and gold stars show all of the beryllium-10 data that we have around the margin. The gold stars show a model which was able to capture those deglaciation ages within 1 sigma. And then the green boxes just show that which experiment was able to capture the biggest proportion of the beryllium-10 data. And so if we walk through them in a sort of paired way, it's easier to see what the main differences are. So if we compare these two climatologies, which we did before when I showed you that table, we find that using a variable seasonality, in this one on the left-hand side, improves the fit in eastern Greenland, whereas once we start getting down into southern Greenland, we see a better fit with the fixed seasonality, although they share the same goodness of fit for 2 parts of southern Greenland. If we use, instead of the ice core climatology, the regional climate model to couple back to the ice sheet, we see that we get the best fit here in the Disco Bay region. So this is the region where we have Jakobshavn Isbrae, as well as an equally good fit in southwest Greenland. And if we are using the Inuitian ice sheet, we see we get a better fit to the data, or the best fit to the data, up in northwestern Greenland, as well as in North Greenland and northeast Greenland here. So what we're able to do by taking each of these scenarios where we've calculated when the ice sheet is deglaciating compared to the beryllium-10 data is we're actually able to start looking at the processes. And so what I'm going to show you now is we're going to split up the ice sheet into its main drainages, just like we've been doing for these subsections. And we're going to take the mean date when the area deglaciated, and so that's shown by this probability density function in the back, which is just a fit to each of the individual ages, which are binned in the gray bars. And I'm going to ask the model, within this drainage basin, prior to the age of deglaciation, what drove mass loss? Was there a lot of loss? Was there a lot of mass lost to interactions with the ocean, or was there a lot of mass lost to interactions with the atmosphere? And that's going to help us see which areas were losing most mass to ocean forcing. And so here's an example where in purple you have the ocean melt, in blue you have the calving, and in red you have the direct surface ablation. So those 3 processes I talked about before that are really critical to the health of an ice sheet. And we're looking at a time series of them in the purple, blue, and red, as well as a sum of them in the green. So you can think of the green line as basically just the total change in volume of the ice sheet as a function of time, which is responding to each of these components, and it's just for one drainage. And so here are 2 examples of the central west coast of Greenland, where we see the most mass actually being lost to direct ocean melting, versus the northeast, where prior to deglaciation, we can see the most melt being lost to surface melt. And you can see the difference between, one difference between these two is that the deglaciation in the west is much later than the deglaciation in the east, which is what we're seeing in the data and which is what the models are able to reproduce when we use our different experiments. And so here, we can do that for all of the experiments that I just ran. And I'm going to plot the individual contributions as these pie charts. And basically, when you have more red, it means that the ice sheet lost more mass to surface melt during the deglaciation. And if you have more purple and blue, it means those oceanic processes at the margin were playing a much bigger role. We look at all of these different scenarios and all of these different maps, but what we really care about is which experiment was able to accurately capture the timing of the deglaciation. And if we do that, it reduces which of these scenarios to which of the scenarios is the most likely. In some cases, we have more than one most likely scenario that the data don't let us distinguish between. If we just reduce our analysis to look at those scenarios which best fit the beryllium-10 data, we can map out where ocean melting was dominating and where surface melting was dominating through the last deglaciation. And that allows us to produce a map that looks like this. Here, I've just colored these regions based on what was the predominant driver of mass loss prior to the deglaciation. And you can see that in southwest Greenland as well as in North Greenland, we have direct surface melting dominating that process. Whereas in the other portions, we have either calving or ocean melt, which were the drivers of the deglacial retreat of the ice sheet. So in general, and then in this, right next to it, I've colored in the boxes based on which of our experiments gave us the best fit to the data. And note that there's these two regions where we have very few data points, and so we don't have good constraints that help us determine which of the models is the best. But in terms of the general spatial pattern, what we see is that when we use an Inuitian ice sheet, when we couple to this larger ice mass, we get a better fit to the data in the northern parts of the Greenland ice sheet. And that's likely because this buttressing is playing an important role in delaying the timing that the ice sheet retreats. Along the east coast, using a variable seasonality that accounts for these changes we think occurred from the last glacial maximum to the present in the seasonal temperature cycle gives us the best fit to the data. But as we come around the southern tip of Greenland, we get a better fit when we use different estimates for the seasonality. And in Jakobshavn, we actually get the best fit when we're directly coupling the ice sheet model to a regional climate model. And what this suggests to us is that especially along the southwest coast of Greenland, there were important regional changes, for example, to local sea surface temperatures or to the surface ocean, which were either changing the moisture budget or the temperature variations in a way that's not well reflected by the ice core records that come from the central ice sheet. And interestingly, we are beginning to be able to compare these kinds of observations to modern data. And so in a recent paper by Jeremy Mogino and others, they looked at the last 40 years of ice sheet mass loss from the Greenland ice sheet, so just during the satellite era, and they separated the mass loss components between the mass that was lost directly due to changes in surface melting and accumulation, and the mass that was lost due to changes in dynamic discharge. And these colors, I've taken this from their paper, so these colors are actually different than the ones that I used, but I have annotated them so that you can see. In the places where we see big changes in the mass budget, so the total budget here is shown in purple, the dynamic change, which is related to ocean melting, is shown in red, and the surface mass is shown in blue. It's very different. But what you see is that in southeast, the loss that we've had is really ocean dominated, whereas in the southwest, the change in mass balance has been very atmosphere dominated. And in the northwest, that's one of the places where we see the biggest modern change, and it's being driven by changes in discharge at the outlets. So it looks like we're seeing that the characteristics that drove deglaciation in these different regions might be the same kind of processes that we're going to see begin to drive ice melt in the modern era. If we go further towards the north, we really don't see as much change. Northern Greenland is much colder and hasn't begun to respond as strongly to the anthropogenic perturbation, but perhaps we can use information like this to predict that in northern Greenland, when we see big changes, we're likely to see them related to surface atmospheric processes, whereas the northeast, because that's what it's done in the past, may respond more strongly to ocean forcing. So this was a deep dive into looking at the last 20,000 years and how we can use these sort of exposure beryllium dates to understand the processes that have driven mass change. But these same data have also been used in a more complex way to try to get at the long-term history of the ice sheet. And there was a very shocking or surprising paper that came out in 2016 where people took a bedrock core that had been accidentally drilled as part of an ice core mission in central Greenland, and they had the question, when was the last time this site was exposed? And the expectation was that there would not be a high concentration of cosmogenic nuclides because past work had shown that at least the central part of the Greenland ice sheet had probably been there since sometime in the early Pleistocene, late Pliocene. There was actually a basal date for this ice core that was 2.7 million years old. And what they found completely flew in the face of that. So these rocks from the base of the summit were actually really hot. They had a lot of these radioactive minerals in them. And so the authors here, you're looking at the delta 18O of benthic foraminifera, so interglacial periods up here for the lighter values or the lower values, and glacial periods down here, the higher values. And these data indicated that there were sort of unlimited possible scenarios for ice cover and ice retreat. Because if you only have one observation, you know that when there's no ice, you're gaining isotopes. When there is ice, you're decaying isotopes. But if you don't have other information about when that happened or when that didn't happen, there's infinite possible solutions. And the authors put forward 3 potential solutions that would all fit their data, but all have really different implications for the stability of the ice sheet on our timescales. The 2 extremes being a long period of ice cover when a lot of isotopes were built up about from 1.4 to 1.1 million years ago, followed by total stability of the ice sheet, or brief periods of ice cover during every interglacial of the last 2.5 million years. And these data played in to a long-standing debate about when and how much the Greenland ice sheet has collapsed in order to contribute to past sea level rise. And we sort of saw this in that Andrea Dutton figure at the beginning of the talk, that we're even uncertain about, in the last couple of interglacials, how much ice each of the remaining ice sheets would have contributed to a high stand. But just as a little primer, there are observations of very warm units around Greenland that are dated to the Pliocene and Pleistocene that suggest that there was a total or partial collapse of the ice sheet. But there are also a lot of observations, both from the Eemian, the last interglacial period, and also from previous interglacials, that suggest the ice sheet is very stable, and even during a warm period like the Eemian, we basically had very little melting at the margins. And so there's been this debate, and the observation that the rocks at the bottom of the ice sheet had actually been exposed fairly recently added a really new, interesting perspective to our questions about to what extent the ice sheet has responded to past warmth. The other interesting finding that has come out in the last couple of years is from a lake that I actually worked on during my master's called Lake Elgegikin. The captions are not going to get that. Which is a lake in high Arctic Siberia. It's above the Arctic Circle, and there's a continuous record of sedimentation since 3.3 million years ago. And the key observation in this Lake Elgegikin is that some interglacials appear as super interglacials. They have a different facies that's a sort of a reddish color, and both from pollen and from other temperature records, they're reconstructed as being exceptionally warm. So one of the hypotheses for what might have driven these super interglacials is that there was collapse of either the Greenland or the Antarctic ice sheet, or perhaps both. And so this observation also motivates us towards understanding, did these super interglacials perhaps have a role to play in determining what periods of time the ice sheet collapsed? So there's a lot that we don't know about the evolution of the Northern Hemisphere over the last 800,000 years. However, we can use models and data together to try to come up with scenarios of possibilities and use the observations from these geochemical data beneath the ice sheet as a constraint on which possibilities are the most likely to represent reality. So what we do, and like I discussed before in terms of the benefits of using a coupled modeling approach, is that not only can we reproduce sort of, I don't know, this is wrong, so ignore this, but not only can we look at modern and last glacial maximum ice sheets, we can also look at ice sheets that are much smaller. So you can remember I showed you earlier in the talk that for the modern ice sheet, we're able to capture the climatology of Greenland reasonably well. We can also deglaciate Greenland and look at how that would affect both the temperature and the precipitation. And you can see that during deglacial periods, you get a lot warmer, but you also get a lot more moisture. And we don't know when these past warm climates may have occurred, but we can scale between them using proxy data and then evaluate our simulations against some set of constraints. I explained to you how all of these cosmogenic isotopes work and that simple explanation works really well when we're just talking about exposure. But when we have multiple periods of cover, you also have to start thinking about erosion and the removal of these isotopes. And so one of the things that I did in this chapter of my thesis is wrote in a cosmogenic isotope module into the ice sheet model so that we could couple it with subglacial erosion. And so in the simulations that I'm going to show you, we will be causing isotopes to accumulate in the bedrock every time that the area is ice-free, and then we will be eroding bedrock and isotopes using this parameterization, this very simple parameterization for subglacial erosion, which has a bedrock hardness parameter, erosion efficiency parameter, which is usually set to 1, we just set it to 1, but so is mostly dependent on the sliding speed. You can imagine that if the glacier is sliding, it's eroding either abrasively or picking up chunks of bedrock, and if the glacier is not sliding, the isotope signals can be preserved for a long period of time. In order to run our ensembles, we're going to use 2 proxy records of climate that allow us to scale between these cold and warm scenarios. This is, again, the benthic oxygen isotope record, but here, just looking for the last 800,000 years. And down here, we have 2 high-resolution reconstructions of northern hemisphere climate, one from Lake Elgagikkan, which is this terrestrial site, and another from the North Atlantic, which is a key area of heat transport to the northern hemisphere, and we expect to be sort of related to driving changes on Greenland because of its role as a source of heat. You can see that these proxy records have a similar shape if we look over the last sort of 80,000 years. You have a last glacial maximum and a marine isotope stage 4, and then up into the Eemian. But once we go further than 80,000 years, they really differ in terms of what they show for the surface temperature evolution of the northern hemisphere. And we're going to use both of them in an ensemble sense, as well as this Lasecki-Ramo proxy record to drive a bunch of ice sheet models and then force them to meet certain constraints. Here, these little spaghetti plots are individual ensemble members, and then they're forced by different proxy climatologies, here by that Lake Elgagikkan record, here by that IODP record, and for the Lasecki-Ramo record, we have this one. And I'm going to plot all of these spaghetti and then ask which of these model scenarios is able to meet 4 sea level constraints for the last 125,000 years. The 4 constraints being that we get a match to the present day sea level, we get a slightly smaller ice sheet in response to the Holocene thermal maximum, we have a larger ice sheet during the last glacial maximum, and then we actually constrain the contribution to the Eemian high stand, so right at 125,000 years ago, to be between 3.3 and 1 meters. So here we say that we think we know what the Greenland contribution to the Eemian is. What does that suggest for earlier interglacials? And if we take those records and expand them to 800,000 years, if you can see these records, what you end up with is a very different behavior of the ice sheet. You can see that this is the volume of the Greenland ice sheet. The modern day volume is 7.4 meters. And you can see that using these 2 different proxy records results in changes in both the duration and the timing of past periods when the ice sheet collapsed. This Lasecki-Ramo benthic delta 820 record, it doesn't show very much variability because we're using something that's really smooth and not capturing a lot of the extremes of climate over this time interval. And what we can do with these kind of solutions for the ice sheet cover is come up with these little, I call them Schaefer plots after Jörg Schaefer, but these red here indicating that the summit of the ice sheet is ice-free and we're accumulating isotopes, and the blue being we actually have ice cover. And the most informative way to look at this is actually to watch these evolve, because ultimately what we want to match and what we're matching in both these simulations is the accumulation of these cosmogenic isotopes, which we know what they are in the past, but we don't know the history that's got us there. And so here what you're seeing in the white is the ice sheet that is fluctuating in response to changes in climate, driven by these climate proxy records that are allowing us to interpolate between different climate states. And then you're also seeing in the purple, the places where the ice is moving quickly, so that's where we're getting erosion of these isotopes. And in the background colors, we're seeing the concentration of 10 beryllium atoms that the model is predicting. Note that this is slightly dependent on elevation. That's why we have to couple it to the ice sheet model, because the production of these isotopes is actually larger when you're at high altitude and there's less shielding by the atmosphere. And as these ice sheets fluctuate, the elevation of the bedrock changes. It gets lower after there's been a lot of ice loading, and it relaxes when there's been less ice loading. So we can let these models run, but what we end up with are maps like this. And so each of these barcodes corresponds to one of the histories that is shown in these plots. Both of our simulations get us to this dark black color, which is within the range of uncertainty for the measurements that were made at Summit, but they show very different spatial patterns of where we would expect the isotopic composition of the bedrock to be high and where we would expect it to be low in other regions of the ice sheet. And if you look at the predictions for past sea level, you can see that while they're close to agreement for the present day, they really differ in the total volume of the ice sheet during past interglacial periods, with an agreement that marine isotope stage 11 was likely a period when the Greenland ice sheet collapsed, but disagreements about whether marine isotope stage 7 or 5 was a large collapse of the ice sheet. So this is just to remind you that both of these scenarios now are able to capture what we know is true from the bedrock, but they have really different implications for which of the past interglacials were the cause of these past collapse that led to the accumulation of cosmogenic isotopes. The nice thing about the model is that we can not only predict the beryllium, but we can predict other cosmogenic isotopes. And so this is showing you the ratio that we talked briefly about between 26 aluminum and 10 beryllium. And basically, this is higher when your exposure has been more recent. And the longer that you have ice cover, the more this ratio changes, because these isotopes are decaying at different rates. And you can see that between these two scenarios, which both match the present day, we get very different predictions for what this ratio should be in the subglacial environment. And we actually have ice cores at all of the places where I've plotted on the map, some of which have collected basal material. So in terms of determining which of these scenarios is closer to reality, our hope is that we can provide equally likely scenarios and then further constrain them by the observations that will come from other areas. The last thing that we have been thinking about, and I would be very interested in talking to people about because we're still learning the best way to implement it, is that we can predict the accumulation of isotopes in the bedrock, and we can predict when it's being eroded. And that means we can also track all of that eroded material as it moves into the marine margin. And what's interesting about this is that there are a lot of marine cores as well, where we recover sediments and we can measure parameters that are related to the history of the ice sheet. And we would like to be able to use those kind of records as constraints on the regional scale variability of the ice sheet. And so here I'm just showing the same video as before, animation, but I'm also showing for these 4 different sectors of the ice sheet what we predict in terms of the integrated delivery of beryllium-10. It just stopped, which tells me I should change the slide. Integrated delivery of beryllium-10 to these 4 different margins. And so we're hoping that in the future, these kind of records, the orange being for the Lake Algagikkan-driven record and the green being for the IODP-driven record, that we can actually generate these synthetic proxy records that can be directly matched to records from marine margins that tell us about not just a single spot, but the integrated changes in a catchment. And for my and so this is something that folks have done in select places. This is Paul Bierman's work on a really long time scale, 8 million years, but they were actually able to measure the beryllium-10 in 2 ODP cores off of eastern Greenland and show that you have these variations through time that we would like to be able to match with a model to have constraints on the longer term evolution of the ice sheet. And so this is the conclusions. We find that we can use different proxy records to get equally likely scenarios for the history of the ice sheet, but they're very divergent in terms of the histories that they predict for the most recent time that the ice sheet collapsed and how much it contributed to sea level rise. However, they allow us to identify places where more data will actually be able to help us discriminate between which of the equally likely scenarios are closer to representing reality. And that is a very powerful way that we can leverage observations from the bed of an ice sheet using an ice sheet model to tell us something about its spatial variability through time. It's also a way that we've really tried to incorporate a process-based understanding of what an ice sheet is and how it affects the landscape around it in analyzing a proxy record that also tells us something about an ice sheet. And in the future, we're really interested in not just using these single point observations, but in using observations that give us some spatially integrated information. And so for my postdoc, one of the things that we'll be working on in conjunction with the IODP Expedition 374 objectives is how the delivery of material from different parts of the Antarctic ice sheet might be affected under changing climate scenarios. And so here I've just taken a collapse scenario of the Western Antarctic ice sheet, and I'm showing which proportions of the ice shelf are being sourced from West Antarctica, which are being sourced from East Antarctica, and which are being sourced from the transantarctics up further south. And you can see that as the ice sheet deglaciates, you get more delivery of this East Antarctic ice via the ice shelf. And one of our ideas is that we can use these kind of predictions to compare with something like provenance data and actually fingerprint different ice sheet collapse scenarios as a function of time. And so with that, I will say thank you very much for your time and attention today, and I will be happy to take any questions. Thanks.